Right now, as you watch this, the sun could release a blast so powerful it dumps more energy than billions of nukes, and we'd only get about 8 minutes before the first warning signs even reach Earth. What if I told you a single solar eruption can throw charged particles across 150 million kilometers and still mess with the invisible technology that runs your GPS, your bank transactions, airline routes, and even parts of the power grid? Stay with me, because once you understand what a massive solar flare actually is, you'll stop thinking of it as a cool space video and start seeing it as one of the few space events that can reach into your daily life on a deadline. Here's what makes it so unsettling. The sun is just a star, and yet it can affect you without ever physically touching you. A strong flare can cause radio blackouts over huge regions on the daytime side of Earth. And if that flare is paired with a coronal mass ejection, a CME, a giant magnetized cloud of plasma, it can slam into Earth's magnetic field and pump energy into it like a charging cable from hell. In extreme cases, space weather has knocked out power, like the 1989 Hydro-Quebec blackout, and damaged satellites. And we're more vulnerable now than at any time in history. Thousands of active satellites, non-stop aviation, GPS-guided shipping, precision farming, and financial systems that depend on exact timing. Our civilization is quietly running on space-based clocks. So when a big eruption happens, is it just a spectacular aurora night or the beginning of a cascading tech failure? To understand the risk, you need the normal science first, because the scary part is how normal it starts. The sun isn't a calm ball of fire. It's a boiling ocean of plasma, and plasma drags magnetic fields around like spaghetti in a blender. Sunspots are regions where the sun's magnetic field is especially intense and tangled, like knots in that spaghetti. Over time, those knots twist tighter, and then, sometimes, something snaps. A solar flare happens when twisted magnetic field lines suddenly reorganize in a process called magnetic reconnection. The simplest way to picture it is stretching a rubber band until it snaps. The stored energy releases explosively as light, X-rays, and fast particles. That light moves at the speed of light, so the flare announcement arrives at Earth in about 8 minutes. That's why flares can cause almost immediate effects in the upper atmosphere, especially radio disruptions on the sunlit side of the planet. But a CME is different. A CME is the punch you can't ignore, an actual mass of magnetized plasma thrown outward. It travels much slower than light, often taking roughly 1 to 3 days to reach Earth, sometimes faster if it's particularly quick. So if you're trying to understand what a solar event means for Earth, you have to keep the distinction straight. Flare equals fast radiation, nearly. Instant consequences for radio. CME equals slower arrival, but potentially much bigger consequences for satellites, navigation, and power grids. Now you might be thinking, doesn't Earth have protection? Yes, and that's the part we usually celebrate. Earth's magnetic field creates a magnetosphere, an invisible shield that deflects much of the solar wind and helps protect the atmosphere from being stripped away. It's one of the reasons we're alive. This is where things get strange, because that same shield can become a giant energy storage system. When a CME hits, it doesn't just bounce off. The outcome depends on a detail that sounds almost too simple to be terrifying. The direction of the CME's magnetic field. If the CME arrives with a magnetic field oriented the wrong way, often meaning strongly southward relative to Earth's field, then Earth's magnetosphere and the CME's field can connect like a zipper. Once that happens, energy pours into near-Earth space. The magnetosphere gets agitated, the upper atmosphere heats up, electric currents intensify, and the auroras can expand far from the poles. And the effects don't stay in the sky. The energy dumped into the magnetosphere and ionosphere can induce currents down here on Earth, geomagnetically induced currents, especially through long conductors like power lines and pipelines. That's where the practical risk lives. Transformers can overheat, protective systems can trip in complicated ways, and operators may have to shed load to prevent equipment damage. Up in orbit, satellites can be hit from multiple angles at once. The upper atmosphere expands and increases drag on low-orbit spacecraft. Satellites can accumulate electrical charge and glitch, and higher radiation can flip bits in electronics or degrade solar panels. Aviation can be affected too. Polar routes may be rerouted due to high-frequency radio issues and increased radiation exposure at high latitudes. So how do we know when it's coming? Space weather isn't new. We just built a world that can notice it. In 1859, the Carrington event lit up skies with auroras and disrupted telegraph systems so badly that operators were shocked and paper reportedly caught fire. No satellites, no global internet, still chaos. In 1972, a powerful storm disrupted communications and is often cited as an early warning that solar events can tangle with military systems. In 1989, a geomagnetic storm collapsed Hydro-Quebec's grid in minutes, leaving millions without power. In 2003, the Halloween storms hammered satellites and communications and forced industries to take space weather seriously again. That history pushed scientists and engineers to build warning systems. Today, spacecraft like ACE and DSCOVAR monitor the solar wind from the Sun-Earth L1 point, about 1.5 million kilometers upstream. That gives us a last-chance warning, often tens of minutes, once the solar wind and CME plasma are about to arrive. It's like having a weather buoy out in the ocean before the storm hits the coast. But here's the cliffhanger. That last-chance warning isn't the hard part. The hard part is earlier, predicting what matters most before the cloud reaches L1. Because the true danger isn't just that a CME is fast or massive. The real danger is geometry, magnetic geometry. That's the core truth. A CME can be huge and still cause only mild effects if its magnetic field orientation doesn't couple strongly with Earth's. And a CME that looks less dramatic can still cause serious geomagnetic storms if it arrives with the wrong magnetic alignment. That's why headlines that focus only on X-class flare can mislead you. The flare is the flash. The CME's magnetic structure is the punch. Experts categorize impacts using scales like NOAA's geomagnetic storm levels, G1 through G5, and flare classifications where X-class flares are the most intense category. Those labels help communicate severity, but the nuance matters. An X-class flare can be spectacular and still not lead to a major storm at Earth if the CME misses us or arrives magnetically friendly. Meanwhile, you can get a dangerous geomagnetic storm from a stealthy CME. An eruption with weak flare signatures that doesn't look dramatic on a quick headline scan. That's the first twist. Second twist, the sun doesn't always throw one punch. Sometimes it throws a combo. Multiple eruptions can interact. One CME can plow into another, changing its speed, density, and magnetic structure. Forecasting becomes a moving target, and uncertainty grows right when you want clarity most. Third twist. Our technology is evolving faster than our protection. Mega constellations mean more satellites in low Earth orbit, exposed to atmospheric drag changes and radiation environments during storms. Power grids are more interconnected, so local problems can propagate. Navigation and timing demands are tighter. More systems quietly depend on accurate GPS timing than most people realize. We're building a more space weather-sensitive world at the exact moment the sun is cycling through periods of higher activity. And that's where the controversy lives. How close are we to another Carrington-level event? Scientists debate probabilities because the historical record is incomplete, and modern instrumentation has only existed for a blink of time compared to solar history. The uncertainty isn't comforting. It's precisely why researchers keep pushing for better solar monitoring, better models, and more resilient infrastructure. The goal isn't panic, it's readiness. Because this affects all of us in a way most space stories don't. Space weather is physics, but it's also electrical engineering, atmospheric science, computer science, logistics, and economics. It's transformer saturation and grid stability. It's the ionosphere distorting radio and GPS signals. It's fault-tolerant systems and timing integrity. It's radiation-hardened electronics and autonomous satellite-safe modes. It's airlines rerouting polar flights and operators deciding whether to put a satellite into protective mode before it takes damage. And here's a strange, beautiful pattern interrupt. The same storms that can break technology also paint the most breathtaking auroras on Earth. The universe uses the same mechanism to do art and chaos. The hopeful part is we're not helpless. We can take action. Grid operators can reduce risk with operational changes, monitoring, and protective strategies designed to prevent transformer damage. Satellite teams can command spacecraft into safe configurations. Airlines can reroute when needed. And that upstream monitoring at L1 gives us real, actionable warning, minutes that genuinely matter. So if you hear massive solar flare, don't just picture a fiery explosion on the sun. Picture two clocks starting. One is the 8-minute clock, radiation and radio effects that arrive with light. The other is the 1 to 3 day clock, a moving magnetized cloud that may or may not couple with Earth's magnetic field in the worst possible way. The real question isn't how bright was the flare. The question is there an Earth-directed CME, and what is its magnetic orientation? Because the sun is the reason we're alive, and sometimes it reminds us it's also a star, and when it doesn't have to hit the ground to hit your life. It only has to shake the invisible systems you depend on every day.